All right, well, thank you for that introduction, and thank you all for being here, and thank you for inviting me here. It's been really nice. I'm thoroughly impressed with the station, and as Sam said, I'm hoping to be back here sometime soon. It's always something. Let's see. How do I do that? You have to change the up here. Yeah. Okay, I think we're all good now. So as Sam mentioned, I'm going to talk a little bit about oxygen supply and demand in marine animals and some of the misconceptions, as I see them anyway. There are those who would disagree that they are misconceptions, so we'll have a lively debate perhaps. So ocean warming and ocean deoxygenation, as well as acidification in some cases, are thought to be forcing marine animals to abandon historic territories and move to more suitable waters. So that's the common interpretation. There are a lot of stark predictions, including mass extinctions, and these are more and more based on interpretations of metabolic traits. This imbalance between oxygen supply and demand is thought to impose a boundary on the biogeography of marine species. So as oxygen drops and temperatures increase, those boundaries are compressed. This graph shows maximum metabolic rate in black here and standard or resting metabolic rate in red, both increasing with temperature. And the difference between those two is called the aerobic scope. That's the potential energy available to fuel all activities, including maximum activity like locomotion, which is typically how maximum metabolic rate is measured, but as well as digestion, growth, reproduction, all of those activities must be fueled by the oxygen. Thank you. Yeah, so the maximum metabolic rate sometimes, not always, declines at high temperature, and that is interpreted usually as a loss of the capacity for oxygen supply. Okay, we get it all figured out here. So this aerobic scope, if you can express it in a couple different ways. The absolute aerobic scope, which is this curve here, is the maximum metabolic rate minus the standard or resting metabolic rate, and it typically increases with temperature up to some peak and then declines thereafter. And this peak is often interpreted as a optimum temperature. But you can also express the same data as a factorial aerobic scope, which is the maximum divided by the resting metabolic rate. And that typically declines with increasing temperature, reaching some level that's often interpreted as critical at about the same temperature usually. So when you're expressing it factorially, colder is typically thought of as better, whereas if you're expressing it as an absolute, colder is typically a little bit worse and then declines again with higher temperatures. Active metabolic rate is also oxygen limited below some level, and the line describing that oxygen limitation is typically drawn as a curve like this, which is another aspect of this interpretation that I disagree with, and I've been in some debates with people over, so we'll talk about that. And again, this standard or resting metabolic rate is well maintained down to some critical oxygen level, and the critical oxygen partial pressure is often interpreted as an indication of hypoxia tolerance. That hypoxia tolerance typically declines with increasing temperature. This is an inverse temperature graph, so higher critical oxygen levels at warmer temperatures. And because that typically declines with increasing temperature, that is often interpreted as a loss of oxygen supply capacity as well at warm temperatures. And lastly, there's a long history, more than a century, of measurements of metabolic rates as a function of temperature, and they typically increase with temperature with what's called a Q10 of about 2 to 3. That means for a 10-degree change, you get a doubling or a tripling of the rate. Some have described based on an Arrhenius plot. So this is an activation energy that describes this line in the middle, and some have described that as a universal temperature dependence. This is data for flatfish species that is now in press, and across flatfish species from the poles to the tropics, there's very little change with temperature. So I have some questions about whether or not there is any universal temperature dependence as well, and how we interpret that. I tend to ascribe to this philosophy that was most eloquently written by Ewald Weibel, maybe 30, 40 years ago, where the oxygen transport system evolves to match maximum metabolic rate. So if you are an active animal, you have a higher oxygen supply capacity shown, or if you're an animal living in hypoxia, like these two deep sea species, you have extremely high gill surface areas and blood that's capable of binding oxygen from very low environmental sources. So in that interpretation, biogeography and ecology determine physiology, not the other way around. The data that is available is strongly biased toward coastal marine fishes. There's data for mammals, there's data for insects, there's data for crustaceans and other invertebrates, but by and large, most of the data is for coastal marine fishes. And I think that constrains some of the comparative conclusions that we can draw. And it's also constrained to coastal habitats primarily, which have a strong latitudinal and sea surface temperature gradient, but no oxygen partial pressure gradient. So cold waters tend to hold more oxygen, which some interpret as being better. Animals are going to be less oxygen limited in polar waters compared to tropical waters because the solubility is greater. However, the partial pressure is the same across that entire latitudinal range. And that, I think, is what's important for the critters. I tend to work in open ocean habitats, or at least did until the last decade or so. They vary or differ in a number of important ways. As you go deeper in the ocean, this graph showing 0 to 500 meters, you have strong correlated gradients in oxygen partial pressure and temperature. So animals that live in this tropical depth range only see air saturated water when it's really warm. And if they experience cold temperatures, it's always extremely low in oxygen. You do not find these animals ever in cold water with high oxygen. Another important variable with depth is light. You tend to have sit and wait predation strategies in the deep sea because visual predation is light limited. So you get sluggish animals like the vampire squid or the anglerfish compared to shallow living tuna fish and active calamari. So let's see if this video will play. So this is the vampire squid living at about 700 meters depth off California. The oxygen there is about 5% air saturation. It's about 5 degrees Celsius, and that is as active as that animal ever gets. It's basically gelatinous. If you pick it up, it kind of runs through your fingers. There's not much to it. It has an extremely low metabolic rate, about 2 orders of magnitude lower than this species, which is the jumbo squid, Dicidicus gigas. This is a vertical migrator, as I'll discuss later. It spends nighttime up near the surface where it actively feeds. And in warm, shallow water that's well aerated, it has extremely high activity and a high metabolic rate. These animals get up to about 2 meters long. I'll try to suppress my Americanisms. So if we're talking about oxygen supply capacity, 1 gram of oxygen would supply the jumbo squid at 25 degrees Celsius for about 30 minutes. That same 1 gram of oxygen would supply the vampire squid for about a week at 5 degrees Celsius. So athletic performance selects for high oxygen supply capacity, whereas at the same time, environmental hypoxia selects for high oxygen supply capacity. So in order to get 1 gram of oxygen from surface water, the jumbo squid has to process about 150 liters of water, assuming it could extract with 100% efficiency. And the vampire squid would have to process about 3,000 liters of water to get that same 1 gram of oxygen. So environmental hypoxia selects for high oxygen supply capacity as well. Just for comparison, an air breather could extract 1 gram of oxygen from a very small volume of air. Yet they still get oxygen limited below a partial pressure of 21 kilopascals air saturation. So what can we do to quantify some of these metabolic traits and see where they become limiting or not? So in collaboration with Curtis Deutsch, we published what is usually referred to as a metabolic index. I've modified it some since, and so I don't know if it can still be called the metabolic index, but anyway, it's basically a ratio of supply to demand, supply equaling demand, so that ratio is equal to 1. Demand is just the metabolic rate measured as the rate of oxygen consumption, metabolic rate, and oxygen supply has the environmental component, the partial pressure of oxygen in the environment, and this term, which we call alpha naught, which is the amount of oxygen being supplied by the organism to its tissues per unit of oxygen available in the environment. So if you multiply those two together, it should equal the metabolic rate. The amount of oxygen per unit of partial pressure multiplied by the partial pressure gives you the rate that's being consumed. So what is that? That includes ventilation, the gill surface area, cardiac output, blood oxygen binding, mitochondrial components as well. All of those things factor into this one term, which some people hate. I am not meaning to diminish anybody's work on the mechanisms that go into that. Those are all extremely important as well. This is a modeling exercise with different questions in mind. So we can measure the oxygen supply capacity. So this is a typical respirometry curve. If you put an animal in a chamber and allow it to consume oxygen, it will maintain a relatively constant resting metabolic rate down to some critical oxygen level. This point, if you divide the metabolic rate at that point by the partial pressure, that gives you this alpha naught term. So that's that corresponding point as an oxygen supply measurement. And so as the oxygen declines and the metabolic rate stays fairly constant, you get an increase in that alpha naught. And it increases up to, I was playing with the animations last night, that was fun. You get an increase up to the maximum oxygen supply capacity. So that's the peak there, and then it typically either plateaus or drops off. It'll plateau if it stays along this line. So that alpha, we've dropped the naught, so that's just alpha is the oxygen supply capacity. That's the slope of this line, and it describes the critical oxygen partial pressure for any metabolic rate, at least theoretically. So if we plot our plug PC, the critical oxygen partial pressure, in for PO2, then that becomes alpha instead of alpha naught. So oxygen supply reaches capacity at the critical oxygen partial pressure. However, it also should reach its capacity at maximum metabolic rate. So when you are running at your top speed on a treadmill, your heart's going as fast as it can, you're breathing as fast as you can, you are at your maximum capacity for oxygen supply. Same would be true if you were at rest and we dropped the oxygen down to about 20%, equivalent to the top of Kilimanjaro or some other equivalent mountain. So these two states, the critical pressure or the maximum metabolic rate, are equivalent in that sense. And as I mentioned, maximum metabolic rate, is typically measured during activity. So we can put an animal in a flume like this one and measure maximum metabolic rate, get them to swim at their top speed, measuring oxygen consumption while they do it. You can also chase an animal around a chamber and then quickly transfer it. The results tend to be more variable, but they often work depending on species. And there are some species that will not swim as well as this one does in a flume as well. So it takes some playing around to make sure you're actually at your maximum metabolic rate. Okay, so these 2 points, the maximum metabolic rate at what I'm calling the critical oxygen partial pressure for that maximum metabolic rate, P-crit max, is equivalent to the standard metabolic rate at its P-crit. And if those 2 are equivalent, then this must be a straight line between them. And this is the formula for a straight line. The maximum metabolic rate is equal to the oxygen supply capacity, which is the slope, times the partial pressure of oxygen. So you can predict what the maximum metabolic rate is at any PO2 between those 2 points. So to test this, I went to the literature. This was work published in 2020. So this was my COVID project for the most part. But we gathered data for arthropods, mollusks, chordates, anything with a relatively well-developed oxygen transport system. Sorry, Sam, I don't think this works for echinoderms. Still testing that. We used aquatic and terrestrial species across a huge temperature and size range, and we gathered any species we could find that had these 3 metabolic traits measured at the same temperature. And we found about 50 species that qualified for that. We predicted the maximum metabolic rate based on the oxygen supply capacity measured at rest times the measurement PO2. And we got a near perfect correlation between that predicted and measured maximum metabolic rate. I had to expand the significant digits for my computer not to tell me it was an R² of 1. So I almost didn't believe it at first, but it predicts it perfectly, which tells us several things. Tells us that all of these metabolic traits are related, and we can calculate maximum metabolic rate and aerobic scope at any size, temperature, or oxygen partial pressure. Some have disputed whether that is actually a straight line, not convinced by that, the relationship between those 2 points. So over time, we've gathered more data showing that between 0 and 100%, you do get a straight line, and then it typically plateaus above 100%. For the few that we do have good data above that 100%. So we're growing the database to show that it is actually a linear relationship. There's about 25 species so far. The ones in blue are ones that we've measured in my lab over the last few years. So I've interpreted this to mean that oxygen supply has evolved to match maximum metabolic rate. And the reason I think that it does is pretty well shown by this video. This is shot in southern Florida. This dolphin chases this poor fish. I'm not going to show you the whole video. It goes on for about 20 minutes. And I won't tell you who wins. It's kind of sad. So, but you can see that it's the maximum activity, at least in this case, that's really driving the need for oxygen supply. It's not when this animal sits at rest in some crevice where the oxygen may or may not drop to some low level. For short periods of extremely low oxygen, they can use anaerobic metabolism. But most species do not see their actual critical oxygen level in the wild, at least as far as I can tell. So I'm interpreting this as if you have these 2 points that are equivalent, selection can't be acting on both of them equivalently, or it'd be quite a coincidence for them to end up at the exact same point. And similarly, you can't have this be a curve, otherwise it'd be quite a coincidence for all 50 species that they ended up at the exact same point. So I think oxygen supply is selected to support maximum metabolic rate, and P-crit is a mathematical artifact that tells you aerobic scope, basically. So the other thing you can do is rearrange this equation. Oops. This was just showing that this is a sand dab off California. Each of these points is a observation reported in the OBIS database. just showing that this animal never gets to oxygen levels near its peak crit. It's usually at least 3 times above its peak crit. So you can rearrange that equation so that the factorial aerobic scope is equal to maximum divided by resting, but it's equivalent to the oxygen partial pressure divided by the critical oxygen partial pressure. So if you have 21 kilopascals of oxygen and a critical oxygen partial pressure of 4, you have a factorial aerobic scope of about 5. And it would be equivalent measured either way. If temperature increases, maximum metabolic rate will go up, oxygen supply goes up to meet it, and the critical oxygen partial pressure changes depending on how resting metabolic rate changes. Typically, the resting metabolic rate increases faster than maximum, and so peak crit increases with temperature. And again, that's what's usually been interpreted as a loss of oxygen supply capacity. But the oxygen supply is responding to maximum, not resting. So this is showing 3 species across a latitudinal range. You've got cod, black sea bass, and chromis from the tropics. They have similar ranges of critical oxygen partial pressures. They have similar maximum critical oxygen partial pressures, similar aerobic scopes across that temperature range. It varies from about 7 to 3 factorially. And this is the oxygen supply capacity that goes up because maximum metabolic rate goes up with temperature. So these guys have evolved a higher oxygen supply capacity to meet their higher metabolic demand in warm water. That gives them the same aerobic scope as the other species. All right, so there are some species that live permanently in very low oxygen. We've gathered data on those as well. And this is the theoretical interpretation. So you've got your peak crit max for a species in typical air saturation. If you compare that to a hypoxic species, the oxygen supply capacity will be higher and peak crit max will be lower. Peak crit will also be a little bit lower, but it's the peak crit max that's under selective pressure. So there's the coastal species I showed you before. The oxygen supply capacity correlated with maximum metabolic rate. The relationship there, maximum metabolic rate equals 21. That's in kilopascals times the oxygen supply capacity. So that number is the peak crit max for all of these coastal species. So as soon as oxygen drops below saturation, maximum metabolic rate becomes limited for all those species. For estuarine species that live in variable but lower oxygen, the average is around 11. The slope of this line is about 11. So until oxygen drops to about 11 kilopascals or half saturation, estuarine species don't care about oxygen. They have the same aerobic scope and maximum metabolic rate until oxygen drops below about half saturation. For some of these deep oxygen minimum zone species, they're not bothered by oxygen until it drops to about 3 or 4 kilopascals. All right, so just to give you a kind of, it's not exactly a side story, but so the exception that proves the rule, I guess. So these are all vertical migrators. They live in the Eastern Pacific where the oxygen drops to about 5% saturation or less at 300 meters or so. And they spend nighttime up near the surface where it's warm and oxygenated, and daytime at that 300-meter depth range where it's cold and low oxygen. So the Humboldt squid is the big one. This guy is much, much smaller, but easier to work with for sure. And then krill, that's what I've been working on here as well. They are migrators as well. Frederick was just telling me he was diving with them at night recently, so that's fun. And myctophids are one of the most abundant fishes on the planet. There's even considering a fishery for them, but you have to go out to sea. I can't imagine it's cost effective, and they're tiny. So this is a sound scattering graph showing sonar and the layer of zooplankton is thick enough that it kind of gives you a false bottom. And so they migrate down during the daytime and back up at night. This is from a tag on one Humboldt squid showing the same migration pattern day and night. And the colors are correlated with the temperature there. So we went out to sea last May, and we're going out again in December for 30 days each time. This is the Sally Ride, which belongs to Scripps Institute of Oceanography. It's 73 meters long and has a science crew of about 25. And I've spent at least half my time since I've been here trying to organize people that are on that cruise and get Mexican permission, which is tricky. So we are going to leave San Diego and go into the both California and work in there where it's nice and calm and flat and lovely. We bring everything we own and set it up on the ship. So this is the lab inside the ship. That's my student Alec Timpe, who will be looking for postdocs. Has a lot of respirometry experience. If anyone's interested, he's a wonderkin. We go out with collaborators, including Chris Roman, he's an engineer from Rhode Island, who developed this instrument called the Wire Flyer. It goes up and down. All of these black traces are up and down of this instrument over about 40 kilometers. And it measures oxygen, temperature, has acoustics on it for viewing zooplankton populations. And you get a very detailed description of what the oxygen and temperature look like across that big depth range. This line is where we towed a multiple opening closing net system. So you can open the net multiple times. There's 10 different nets on it. You can open different nets at different points. And so you can tell that where the oxygen is low here, there were relatively few zooplankton. Here they were higher, and here they were low again. So you can get a real glimpse. So this is a trace. So just a few micromoles of oxygen across that depth gradient was noticeable in terms of the abundance of different species of zooplankton. This is a net that I inherited from my graduate advisor. It's older than I am, but it's 100 feet long, has a 10-meter square mouth, and has oxygen temperature sensors on it as well. The length helps, so if all the water that goes into the mouth of the net has more surface area to leave the net, and so the animals don't get plastered against the side of the net. So we can catch animals from 4,000 meters alive and in pretty good condition. We bring respirometers of all different sizes and shapes, so we can measure copepods to small squids. This is a mini flume. This is a homemade bigger flume, or actually not, this wasn't the flume, but flow-through respirometry system that we measured jumbo squid in, which are a pain because they tend to ink. And this is a kind of cobbled together temperature and oxygen control system. So preliminary data from this is showing that the oxygen supply capacity of all these vertical migrators is very high, but it's insensitive to temperature. So whereas the oxygen supply capacity increases across the temperature range for most coastal fishes, it's pretty constant for these migrators. So they have high oxygen supply capacity in the cold, low oxygen water, where they don't need much activity, and they have high oxygen supply capacity in warm, shallow oxygenated water where they're much more active. So they're effectively deep sea species when they're in cold water, and they're shallow living species when they're in warm water. So we can calculate the aerobic scope across that temperature range. They have very low aerobic scope when they're at cold temperatures, and they open up when they're in warm water. These different curves are different regions where the squid is found, the oxygen temperature relationship. So here they have low aerobic scope, but they're temperature limited, not oxygen limited. There's plenty of oxygen here, but they still have low aerobic scope because the temperature is cold. Here in the Eastern Pacific, the oxygen is a little bit low, so their aerobic scope would be suppressed a little bit here by oxygen. But in general, they have much higher aerobic scope in warm water. And I've shown you this one already. This is the squid being very active, just to remind you. this is them at 300 meters shot by the remotely operated vehicle at the Monterey Bay Aquarium Research Institute. So in cold water, they are slugs. The submersible is brightly lit, and I think that triggers them to do a little bit of feeding, but for the most part, I think they sit down there and are not actively feeding. But these are the myctophid fishes that do something similar. They vertically migrate and are pretty inactive during the daytime and much more active at night. So we put a hypothesis out that this sort of inverse effect of temperature on aerobic scope effectively makes cold water an energetic barrier for these animals. So this is the native habitat now and in the future, where so in the tropical waters, temperature at the surface will get a little warm and compress their habitat, and low oxygen is expanding a little bit. So their metabolically available habitat in the future will be compressed a little in the tropics, but not much. This is to the north and south. So off California, for example, these squids will sometimes migrate up off California waters, but they're generally cold limited in that entire range. But if you just increase the temperature a little bit, they have a much broader available habitat to them. And you'll see this during El Niños. Those squids show up off California and wreak havoc on the fisheries there and freak all the divers out. All right, so I will stop there and take any questions.
So thank you. So we're going to take questions first in the room, but if you have questions online, just raise your hand and I will alternate. So let's start inside the room. Questions, comments?
Yeah, I have a long list of it's fascinating stuff, really cool. I have no problems with your suggestions here, but there are a few things that I really found extra interesting. You said that hyperoxia doesn't increase MMR in some of the species you found. I know some others that have found increase in MMR in hyperoxic waters. And
so there's a couple of things going on there. I think firstly, you will get maybe a slight increase, 5 to 10%, because there's just going to be more oxygen dissolved in the blood. But the respiratory proteins, hemoglobin and hemocyanin, are generally saturated at 100% of air saturation in the water. And so there's not much room to increase that. And I think the other issue is that a lot of people start their measurements for maximum metabolic rate at air saturation or just below, and the oxygen will drop in the chamber down to 90. I think one review paper suggested keeping the oxygen above 80% or something. So by the time you reach 80%, your maximum metabolic rate has dropped already by 20%. And so if you compare that rate to something in hyperoxia, you're really not comparing an equivalent measurement. I don't rule out the possibility that there are species that experience hyperoxia enough that there's selection for them to have higher metabolic rates in that hyperoxia, but I haven't seen any really convincing evidence yet that it does.